Turning to another sort of indeterminate forms for limits, let's talk about powers. What I mean by that is a limit of an expression that can be written that way, where I take a certain function of x and raise it to a power that depends on x. So something of the form f of x to the g of x, where x is approaching a. A may be a finite or infinite number. So there's three kinds of indetermination for powers. We could have f and g both approaching 0, right? Both the base and the power approach to 0, and we get an indeterminate form of the type 0 over 0. We're going to see in a second exactly why this is indeterminate. Another possibility that leads to indetermination is if the base f of x goes to infinity while the power g of x goes to 0, and we get an indeterminate form of the type infinity to the 0. The third possibility is that the base f of x goes to 1 while the power g of x goes to infinity, and we have an indeterminate form 1 to the infinity. It might not be clear to you at first glance why these things are indeterminate, but let's take a look at what f of x to the g of x really means. One way to rewrite that, in fact by definition of this type of powers, it's e to the power g of x multiplied by ln of f of x. So whether the limit is something indeterminate or not depends on the limit of g of x times ln of f of x. Now let's look at the three cases again. In the first case, f and g both go to 0. If f goes to 0, that means ln of f goes to negative infinity. And I multiply by g of x going to 0, so I have an indeterminate product 0 times infinity. Similarly, in the second case, if f goes to infinity, so does ln of f, and g of x goes to 0, so I have again indeterminate 0 times infinity. In the third case, if f goes to 1, then ln of f goes to 0, and g of x goes to infinity, so the product is again an indeterminate product of the type 0 times infinity. So in each one of these three cases, the power inside the exponential is an indeterminate product of the type 0 times infinity. But we know how to deal with those. We've seen that we can rewrite products as quotient, then use the rule of de L'Hopital to obtain the limit. So we can obtain the limit of what's in the exponent. And then we can plug the result inside the exponential function to get the limit for the power f of x to the g of x. And that's exactly what we're going to do to lift indetermination in these kinds of cases. So let's take a look at a few examples. In the first case, we're looking at the limit at 0 from the right of tangent of 2x to the power x. So according to what we just have seen, the first thing we're going to do to deal with this type of problems is rewrite the power as a power of the Euler number e. Namely, in this case, our expression can be rewritten as e to the x ln of tangent 2x. And we're going to focus first on the limit of what's inside the exponential function, namely x ln of tangent 2x. So we're looking for the limit at 0 from the right of x ln of tangent 2x. That's an indeterminate product. We're going to rewrite it as a quotient. So I can write it, for instance, as a limit at 0 of ln of tangent 2x divided by the reciprocal of x. Then when x goes to 0, tangent 2x goes to 0, and therefore ln of tangent 2x goes to negative infinity. And 1 over x goes to 1 over 0, in other words infinity, so we have an indeterminate form of the type infinity over infinity. So we can use the rule of de L'Hopital, and that means that the limit is the same as the limit at 0 of the quotient of the derivatives. So let's examine the derivatives. The derivative of ln of tangent 2x is going to be the derivative of tangent 2x divided by tangent 2x. But the derivative of tangent is secant squared, so using the chain rule, the derivative of tangent of 2x is secant squared of 2x multiplied by the derivative of 2x, which is 2. So we get at the top 2 secant squared 2x divided by tangent 2x. Then we divide that by the derivative of 1 over x, which is negative 1 over x squared. Now we can rewrite that differently. Secant squared is really 1 over cosine squared. So rewriting things, what we obtain here is negative 2x squared divided by cosine squared 2x tangent 2x. Now tangent 2x is really sine 2x divided by cosine 2x. So when I multiply that by cosine squared 2x, I can cancel out one of the cosine 2x, and I obtain the limit of negative 2x squared divided by cosine 2x sine 2x. Now remember that if you have 2 cosine x sine x, this is sine of 2x, double angle formula for sines. So in this case is cosine 2x sine 2x, it is 1/2 of sine of twice the angle. In other words, 1/2 sine 4x. So if I have 1/2 at the bottom, it's like multiplying by 2 at the top, and therefore I get 2 times 2x squared, that's 4x squared at the top, and sine 4x, right, sine 2 times the angle 2x, at the bottom. All this to say, our limit is the same as the limit at 0 from the right of negative 4x squared over sine of 4x. If I plug 0 in this, I get 0 at the top, I get sine 0, which is 0 at the bottom. So, this is an indeterminate form of the type 0 over 0. But I can use the rule of de L'Hopital for something like that. So we obtain the same limit as the limit of the quotient of derivatives. Derivative of the top is 8x, of the bottom is 4 cosine 4x. And now if I plug x equals 0 in this, I get 0 at the top, and I get 4 times cosine 0, in other words 4 at the bottom. 0 over 4 of course is 0, so this is our limit. Now this is not the limit that we are seeking, this is the limit of what we have in the red circle, in the red ellipse I should say. In other words, it's a limit of x ln of tangent of 2x, but what we want is a limit of tangent 2x to the x, and to get that we just need to plug in the limit that we have obtained for the exponent inside the exponential function. So in other words, we get for the limit e to the 0, because 0 is the limit of x ln of tangent 2x, and e to the 0 in this case is 1. So 1 is the limit of tangent 2x to the x at 0 from the right. Moving to the second example, we're looking for the limit as x is going to infinity of e to the x plus x, all of this to the power 1 over x. So what we have in the exponent goes to infinity, what we have in the base goes to infinity, and the exponent 1 over x goes to 0. So we have an indeterminate power of the form infinity to the 0. As usual, we're going to rewrite that as a power of the Euler number e. Specifically, it is e to the power 1 over x ln of e to the x plus x. And we're going to seek the limit of the exponent. Namely, the limit at infinity of ln of e to the x plus x over x is an indeterminate form of the type infinity over infinity, so we can use the rule of de L'Hopital to the effect that the limit is the same as the limit of the quotient of the derivatives. For the derivative of the top, we have log of a function, we get the derivative of that function, e to the x plus 1, divided by the function, e to the x plus x. We divide that by the derivative of the bottom, which is just 1. So we obtain the limit of e to the x plus 1 over e to the x plus x at infinity. It is again an indeterminate form of the type infinity over infinity, so we can use the rule of de L'Hopital again. Derivative of the top this time is e to the x, of the bottom is e to the x plus 1. This is again an indeterminate form of the type infinity over infinity, so we can use the rule of de L'Hopital again. And now we get that the limit is the same as the limit of e to the x over e to the x, which is the limit of the constant function 1, so it is 1. So what we have obtained here is that the limit of what's inside the limit of the power is 1, and therefore the limit of our expression e to the x plus x to the power 1 over x is really e to the 1. And e to the 1, of course, is the Euler number e. One more example to conclude. The limit at infinity of x plus 1 over x to the power 1 over x. Again, what's in the parentheses goes to infinity and the power goes to 0. So this is again an indeterminate form of the type infinity to the 0. As usual, we rewrite the expression as a power of the Euler number e. In this case, e to the 1 over x times ln of x plus 1 over x. And we look for the limit of the exponent. Namely, the limit at infinity of 1 over x ln of x plus 1 over x. So this is a quotient of the form infinity over infinity because x plus 1 over x goes to infinity, and x goes to infinity, 1 over x to 0. And we plug that inside the log. The limit of ln at infinity is infinity, so the top goes to infinity, the bottom does as well. So this is the kind of indeterminate forms to which the rule of de L'Hopital applies. And so we find that the limit is the same as the limit of the quotient of the derivatives. The derivative of the bottom is going to be just 1, so I didn't write it. The derivative of the top is the derivative of the function inside divided by the function inside. So we get 1 minus 1 over x squared divided by x plus 1 over x. If we look at the limit of this expression when x goes to infinity, then 1 over x squared goes to 0, so the top goes to 1. And for the bottom, 1 over x goes to 0 and x goes to infinity, so the bottom goes to infinity. So we have the top going to 1, the bottom going to infinity, and therefore the quotient goes to 0. This is not the limit of the expression x plus 1 over x to the 1 over x, but only the limit of the power of the Euler number. So we have to plug that in order to get the limit of this expression. And what we obtain is e to the limit of the power, in other words, e to the 0, which is 1. Now it's time for you to practice with homework.